Hello everyone. So this is a question from JEE Mains 2026, 28 Jan morning. 20 decimeter cube of an ideal gas X at 600 and zero point 0.5 megapascal undergoes isothermal reversible expansion until pressure of gas is zero point 0.2 megapascal. Find work done, change in internal energy, change in enthalpy and heat, and some values of log 2 and log 5 is given to us. Okay, so in this, few things are very important to us. First is the volume is given and it's a ideal gas. Then the temperature is given to us, then pressure is given to us, then isothermal reversible expansion, and final pressure is given to us. And these are the things that we are supposed to find. Okay, so the chapters involved is thermodynamics, and so let's use the details that have been given to us. Okay, first they have given us that we have 20 decimeter cube of an ideal gas. So we know that 1 dm cube is equal to 1 liter. So therefore 20 dm cube will be equal to 20 liter. Okay, why am I converting decimeter cube into liters? Because when we do calculations we have to use R, and R is 0.0821 liter atmosphere Kelvin inverse mole inverse. Okay, so if we convert the volume into liters it will help us because R itself is in liters. Yeah, so this is the volume which is given to us. Next, they are saying that it's an ideal gas, very important. Okay, you will see this information is very important, that we have an ideal gas, it's not a real gas. Okay, so it follows the ideal gas law. Cool. Then temperature is given to us. Okay, 600 Kelvin, fine, 600 Kelvin. And the initial pressure is given to us, it is 0.5 megapascal. Okay, so we know that 0.5 megapascal is equal to 0.5 into 10 to the power 6 pascal. Okay, and since, as I mentioned, the value of R is in atmosphere, so therefore it was important to know how to convert pascals into atmosphere. So the conversion is 1 pascal is equal to 9.869 into 10 to the power minus 6 atmosphere. Okay, so this will be really useful for us. Cool. Then undergoes isothermal reversible expansion, so important. Okay, so the process that it is undergoing is isothermal reversible expansion. Okay, so what is the meaning of isothermal? So this implies that the temperature is maintained constant throughout the process. Okay, then they have said that it is reversible. So the meaning of reversible is that in a reversible process we carry out, it is carried out infinitesimally slowly. Okay, infinitesimally slowly, so that all the changes in the process can be exactly reversed. All changes in the process can be exactly reversed, and the system is in a state of equilibrium with surroundings at every stage of the process. And system is in equilibrium with surroundings at every stage of the process. Okay, so in a nutshell, in a reversible process it is infinitesimally slow, it is very very slow, so that all the changes in the process can be exactly reversed. And since it is very slow, system is always in a state of equilibrium with surroundings, okay, at every stage of the process. Okay, we rarely observe reversible process in our day-to-day life. Okay, to imagine or to think of a reversible process, what you do is you think of a piston. Okay, and this piston has a gas inside it. Okay, and let's say that we have a pile of sand above the piston. Okay, so there are two kinds of pressure. So here what will happen, the pile of sand and the piston will exert a external pressure on the gas. So let us say that is external pressure, P external, and let us say the gas also has its molecules. So the gas molecules will also be exerting a pressure on the piston back. So that is known as our internal pressure, or you can be written as P internal. Okay, so the condition for reversible expansion, because in the question they have mentioned that it is reversible expansion. Okay, so for the gas to expand, obviously the external pressure has to be lesser compared to the internal pressure. Only then it rises up, or leads to expansion. So that's why the necessary condition for reversible expansion is P external is equal to P internal minus dP, right? So you can see the external pressure is lesser than the internal pressure by a very small amount. That's why it is a reversible process. So since the external pressure is less, so therefore the gas will expand. So the small amount of work done, okay, we represent it by delta W, and since it is a path function, we are using this symbol and not this symbol. Okay, so when the gas expands through a small volume dV, okay, so the work done when the gas expands through small volume dV against the external pressure P external, so that will be equal to dou W is equal to minus P external into dV. Okay, so this is the small amount of work done that the gas has done when it expands through a small volume of dV and against the external pressure P external. Okay, and this formula is used for expansion as well as compression. Okay, don't worry about the signs, the formula takes care of itself. Okay, so this is a formula which is true for expansion as well as compression. Okay, so the final answer will take care of itself. Okay, so for example, let's say we have a system. Okay, so in the system, so I'm talking about the sign convention. In the system, whatever comes in, let's say heat is coming in, or let's say someone is doing work on the system, so that is going to be positive. Okay, heat coming in and work done on, that is going to be positive. Whatever goes out of the system, that is heat going out, will be negative, and the system doing work will be negative. So the final answer of work done will be negative if the system does work. If the work is done on the system, the final answer will be positive, right? But the formula is always minus P external into dV. After putting all the values, the final answer will take care of itself. So we need not worry. Okay. Now, since we said that it is reversible expansion, so we can write P external is equal to P internal minus TP, and we can substitute this value of P external in this equation. So dou W, or the small amount of work done, will be minus of P internal minus dP into dV, right? So this is equal to minus P internal into dV plus dP dV. Now these are very small quantities which are multiplied to each other, so that's why this can be neglected. Or we can say that the small amount of work done is equal to minus P internal into dV. So this is the small amount of work done when the volume is small volume, that is dV, right? So the total work done when the gas expands from initial volume V1 to final volume V2. Okay, so total work done when gas expands from V1 to V2, initial volume V1 to final volume V2, will be obviously the integration, that is work done will be equal to minus integration of V1 say V2 and P internal into dV, right? And this is the value of total work done, and this is true for any reversible process. Okay, whether it is isothermal, adiabatic, isobaric, isochoric, it is true for any process. Okay, now we know that if we have an ideal gas, for ideal gas, since it is given to us, PV is equal to nRT, right? So this P internal is nothing but the pressure of the ideal gas. So I can write P internal is equal to nRT by V, and I can substitute this here. So the work done formula becomes minus integration V1 say V2 nRT by V into dV, right? Now in our case they have mentioned it is isothermal reversible expansion, and when they say isothermal, that means the temperature is going to be constant. So therefore we can take nRT out from the integration because it is a constant. So therefore this equation can be written as minus nRT V1 to V2 1 by V dV. The integration of 1 by V is ln V, so this is minus nRT ln of V V2 V1, okay, which can be written as minus nRT ln of V2 minus V1, sorry, ln of V2 minus ln of V1, and which ultimately can be written as minus nRT ln of V2 by V1, because we know that ln of A minus ln of B is equal to ln of A by B, right? So to remove the negative sign, we can also write it as nRT ln of V1 by V2, okay? And at constant temperature, we can use Boyle's law, and Boyle's law, according to Boyle's law, we know that P1 V1 is equal to P2 V2, right? So V1 by V2 can be written as P2 by P1. So this formula can be changed into work done is equal to nRT ln of P2 by P1, okay? So we are doing this because, you know, in our question they have given us final pressure and initial pressure, right? So we can easily calculate the work done. In the question, so we have been given volume of initial volume is given to us as 20 liters. The temperature is given to us as 600 Kelvin. Initial pressure is given to us as 0.5 into 10 to the power 6 Pascal, and so we need to convert it into atmosphere. So this is 0.5 into 10 to the power 6 into 9.869 into 10 to the power minus 6 atmosphere, right? So we are left with, so this is basically 0.5 into 9.869 atmosphere, right? Okay, so we know the temperature, we know the gas constant, we know final pressure, we know initial pressure, but we don't know the number of moles. To know the number of moles, we can use these values, that is PV will be equal to nRT, right? So pressure is, we know, the initial pressure is 0.5 into 9.869. Volume given to us, initial volume 20 liters, will be equal to N into R is 0.0821 and temperature is 600. So therefore N value will be equal to 0.5 into 9.869 into 20 divided by 0.0821 into 600. Okay, so when we do this calculation, we get N is 4.9345 divided by 2.463. And upon further calculation, this comes out to be 2.0034, which is approximately 2. So the number of moles of the gas is 2. Okay. Now in this question, the initial pressure is given to us, or you know, P1 is equal to is 0.5 megapascals, and P2 is given to us as 0.2 megapascal, right? So we have to calculate the work. Now we have derived the formula. The formula is this, that work done is nRT ln P2 by P1. Okay, cool. So we'll write this down again. So work done is nRT ln P2 by P1. Okay, cool. And so we'll write down n is 2. We just calculated n is 2. So 2 into, now here very important, the R value that we are going to use is not 0.0821. Okay, R value that we are going to use in this is 8.314 because this involves work or energy term, joules. So whenever joules term is involved, the unit of R that has to be used is 8.314. In the previous gas equation, we use R value as 0.0821 because here pressure, volume terms are there, right? So I hope this is clear. Okay, so be careful which R value that you are going to use. So in terms of joules per Kelvin, R is 8.314 joules per Kelvin. We know the temperature, it is 600 into ln of final pressure is 0.2 divided by 0.5. Cool. And obviously, you know, in our case, they have given us the value of, let's see the question. They have given us the value of log 2 and log 5. So that's why we have to convert our equation into log. Okay. So to convert, we know, right, ln of x base e is equal to 2.303 log of base 10 x. Okay. So we will rewrite this 2 into 8.314 into 600 into 2.303 log of 0.2 by 0.5. So 0.2 by 0.5 is not basically 2 by 5, right? And log of 2 by 5 is basically, so we can write this as 2 into 8.314 into 600 into 2.303 into, and log of a by b is log of a minus log of b. So this is log of 2 minus log of 5. And log 2 value is given to us 0.301. Log 5 value is given to us 0.6989. When we do the subtraction of these two, we get minus 0.3979. So basically work done is 2 into 8.314 into 600 into 2.303 into minus 0.3979. And when we do the calculations, it comes out to be minus 9142.377 joules, or which can be, you know, approximated as minus 9.1 kilojoules. Okay, so this is the work done. Next, we have to talk about the internal energy. Now, in this case, we have been given ideal gas. Okay, and we should know one important information, that in the case of ideal gas, internal energy is a function of temperature only. Okay, U, that is internal energy of ideal gas, is a function of temperature only. So according to mathematics, you can write it as U is a function of temperature only. And in isothermal process, as it has been mentioned, temperature is constant. So there is no change in temperature. If temperature is not changing, the value of U will also not change. So that's why, you know, delta U, that is change in internal energy for an ideal gas in an isothermal process, is always equal to 0. So therefore, read the question properly. Okay. Next, we have to talk about delta H. Okay. So we know that H is equal to U plus PV, right, according to thermodynamics. So the change, so therefore change in H will be equal to change in U plus change in P into V, right? So this is, you know, chain rule. And we know that for an ideal gas, PV is equal to nRT, right? And it has been mentioned that, you know, it's an isothermal process. So if it is an isothermal process, then the value of N into R into T is not going to change. That means PV itself is a constant. So therefore, change in PV will be equal to 0, right? So therefore, for an ideal gas, and when it undergoes isothermal process, whether it is, you know, compression or expansion, delta H will be equal to delta U, because the temperature is constant, so nRT will be constant, so PV is constant, so change in PV is 0, right? So delta H is equal to delta U, and we have calculated that delta U is equal to 0. So therefore delta H will be also equal to 0. Okay, to calculate heat according to the first law of thermodynamics, we know that delta U is equal to Q plus W. In this, in this case, we have an ideal gas and isothermal conditions. Delta U will be equal to 0. So 0 is equal to Q plus W. We have calculated the work done, that is minus 9.1 kilojoules, right? So Q will be equal to minus of W. So therefore Q will be equal to 9.1 kilojoules. So therefore option A will be correct. Okay, so the value of delta U is 9.1 kilojoules. The value of delta H is 0. The value of delta U is 0. And the value of work done is minus 9.1 kilojoules. Okay, thank you.